In partial fraction decomposition, or expanding fractions, you take the roots of a fraction and create separate terms for each root. Here is a solved example. Similarly, 3s plus 5 over s minus 3 times s plus 5 expanded to a over s minus 3 plus b over s plus 5. Solving for a and b, multiply both sides by the denominator s minus 3 times s plus 5. The variable s is red, and the s terms are underlined in blue, and the constant terms are underlined in yellow. Gathering the s terms together, you get 3s is equal to as plus bs, or 3 is equal to a plus b. Gathering constants, you get 5 from 3s plus 5, so 5 is equal to 5a minus 3b. Now you have two equations and two unknowns, a and b, and the equations 3 is equal to a plus b, and 5 is equal to 5a minus 3b. And solving those equations for a and b, you get b is equal to 5/4 and a is equal to 7/4. We started out with 3s plus 5 over s minus 3 times s plus 5 is equal to a over s minus 3 plus b over s plus 5. We solved for a and b, and we got 7/4 is equal to a and 5/4 is equal to b, and here's our solution. And now here's the check. What about repeated roots? You would write 1 over x minus 3 squared times x plus 5 as a over x minus 3 plus b over x minus 3 squared plus c over x plus 5. Another example, 1 over x minus 3 squared times x plus 5 cubed is equal to a over x minus 3 plus b over x minus 3 squared plus c over x plus 5 plus d over x plus 5 squared plus e over x plus 5 cubed. For a complex root, the denominator is 1 degree higher than the numerator. Here the denominator's highest term is x cubed, and in the numerator the highest term is x squared. And below this is a repeated complex root and how you would expand it. In this example, the numerator's highest term, x to the fourth, is higher than the denominator's highest term, x squared, so you have to divide the numerator by the denominator, and you get x squared minus 2x plus 19, plus the remainder, which is minus 68x plus 285 over x squared plus 2x minus 15, and you can expand that with partial fraction decomposition.